and thank you for coming. So this is Johnny Hui, who is also here. So today, I want to tell you a little bit more about submodular maximization. So we've already heard about submodular set functions, so let me define them. So modularity is a property of set functions. So we have a finite ground set and a function that assigns a real value to every subset. And we say submodular if it has diminishing returns. So that means that the marginal gain that we get, the additional gain from any given element, only decreases as our sets grow larger. So one very nice example of a submodular function you're already probably familiar with is the coverage function. So imagine we have a collection of sets, and if you look at a subset of them, their coverage is the number of distinct elements that they contain. And this turns out to be submodular, so it has diminishing returns. So another very nice example is the cut function of a graph. So here we have a graph with edge weights. And if we look at a set of vertices, their cut value is the total weight of the edges that are leaving. So the cut function is also submodular. So in this talk, I'm interested in maximizing submodular functions subject to any constraint. So we could have a constraint like a cardinality, where we want to pick at most k elements, or a matroid, or anything. The function is not necessarily monotone. So what is one of the main motivations for these problems? So they're of independent mathematical interest, but they also have some very nice applications. So recently, they've been used in a variety of settings in machine learning and beyond. So they turn out to be very useful for large data summarization. So for example, if you have images or video, it's also very useful for things like finding relevant items on the web, so web ranking, and a variety of other applications. And one of the most powerful approaches that we have for understanding submodular maximization problems is via a very powerful paradigm, which we call the continuous relaxation and rounding. So this approach is very general, and what it tries to do is to take a discrete problem like our submodular maximization and turn it into a continuous optimization problem. So we want to relax our constraints and maybe change our function and get a continuous optimization problem, and solve this continuous optimization problem, get a fractional solution, which we then hope to round back and get an integral solution. So in this talk, concretely what this would mean for us is the following. So one thing that we need to do, since submodular functions are discrete, is that we need to extend them to the continuous setting. So I'll use the multilinear extension to do that. So I'm not going to define what the multilinear extension is in this talk, because we don't need to know it. But you can think of it as it's a continuous extension of our function to the continuous domain. And I'm also going to relax our constraints, so combinatorial constraints will become convex polytope constraints. Okay? So this gives us a relaxation for our problem, which is called a multilinear relaxation, where we want to maximize the multilinear extension subject to some polytope constraints. So two important things that I like to mention about this relaxation is, first of all, that this is not a tractable problem. So the continuous problem itself is NP-hard. So unfortunately, the multilinear extension is not concave. It's neither convex nor concave. But it does have some concave aspects. So in particular, it's concave along positive lines of direction. So this provides us an interface to convex optimization, but it's a bit more limited. And in this talk, I'll focus on the first part of the framework, where we focus on solving the continuous problem. So I'll only be trying to solve the continuous optimization problem, and I will not discuss the rounding. So this will be the main focus of the talk. Good. So let us jump in and try to understand how to solve this continuous optimization problem. And here's a very nice approach to do this. So Jan Vondrak proposed the following algorithm, which is inspired by both the greedy algorithm and greedy and SN. And we call it the continuous greedy algorithm. And let me tell you what it does. So what we do is that at time 0, we start at the origin, and we'll grow our fractional solution over time. So the clock will run from time 0 to 1 continuously. And at every time step, we'll update our solution. And the way we do that is by computing the gradient at the current point. And this gradient gives us a linear approximation of our function that is quite good locally. And using linear optimization of our polytope, we can even find the best direction with respect to this linear approximation. So we can find the vector v that maximizes the linear approximation. And we use this vector to update the solution. So we'll move according to this vector, so we'll increase the fractional solution at the rate given by this vector. Okay? So this is the continuous greedy algorithm, and it traces a curve from the origin to some vertex of our polytope in this fashion. And remarkably, what Jan Vondrak was able to show is that if our function is monotone, meaning that the value on supersets is at least as big than the value on any subset. So if the value can only increase, then the continuous greedy algorithm achieves the optimal 1 minus 1 over e approximation. Okay? So for monotone function, we have a 1 minus 1 over e approximation. And I want to give you a little bit of intuition on why that is. So for this, let's take a minute to look at this continuous greedy dynamics and see what is going on. So the dynamics tells us how the fractional solution is growing over time. To understand the approximation, we need to understand how the fractional value is growing over time. So the dynamics of the fractional value. And how do we understand that? Well, there's a very simple rule called the chain rule that allows us to relate the gain in fractional value to the gain in the increase in the fractional solution. It's simply the gradient times the increase in fractional solution. So it's the gradient times this direction v according to which we move. Okay? So throughout this talk, I'm going to talk about this kind of inner product as the gain of our direction. So this is how much we gain. But how do we relate it to the optimal solution? Well, a very simple idea is that the optimal solution itself is a candidate direction. It is in the polytope. And using submodularity and monotonicity, we can actually relate the gain of our current direction to the optimum. And what it tells us is that we have this concavity-like property, where our gain is actually at least the optimum function value minus f of x. Okay? So this gives us the dynamic of, that describes how the functional value evolves over time. So if we simply solve this differential equation, what it tells us is that the function value starts at 0, and it grows exponentially over time. And when time reaches 1, we reach minus 1 over e. Okay? So this is very nice. But how about non-monotone functions? So this crucially relied on monotonicity. And in fact, if the function is non-monotone, greedy doesn't do so well. And greedy could easily fail. And intuitively, the reason why greedy fails when the function is non-monotone is that initially, it could pick a bad element that could completely ruin our solution because of non-monotonicity. So intuitively, if we want to do something like greedy, then what we would want to do is not to commit to elements too early on before we know how good they'll be in the end. Okay. So what's the concrete way to do this? So here's a very nice idea coming from the work of Feldman et al. So what they suggest is that, so let's not try to commit too early. So let's, you can think of it as, let's put a barrier at 1 and try to stay away from picking elements early on. So concretely, what they suggest to do is to slow down the growth by multiplying by 1 minus x. So if the coordinate xi is already quite high, we only grow by almost 1 minus xi. So the coordinates that are high grow less. Okay. And it turns out that this is all we need. So with this modification, now the continuous greedy algorithm actually achieves a constant factor approximation, and in fact, it's 1 over e. Okay. And what is the intuition behind that? So again, we can take a look at how the function value is increasing over time. So the function value dynamics. So before we could lower bound this by f of ob minus f of x. So now we can no longer do that, but we can do something similar. So now a lower bound on our growth is actually given by this point, which is not the optimum, but it's the pairwise maximum between the optimum and x. So I call that x or odd. So after multiplying by 1 minus x, we can show that the function value is increased is at least f of x or odd minus f of x. Okay, so this looks promising, but a priori, this could be much worse than obs because of non-monotonicity. Because this is not the optimal solution. It's the optimal solution with some additional spurious mass put in by x. So this could actually be much worse than ob. But something interesting happens, though. So we can say something about how this quantity relates to f of ob by looking at the norm of x, the infinity norm of x, so the maximum coordinate. So we can only say that this value is at least 1 minus the norm of x times f of ob. So in other words, if the coordinates of x are small, then we do get almost f of ob. Not quite, but almost f of ob. So if we can control the norm, then we can control the value. And this continuous greedy dynamics, because we only increase by 1 minus x, also controls the norm. So it controls our norm, which in turn controls the value, and this is what gives us 1 over e. Okay? Good. So have this very nice picture where now we have a continuous greedy algorithm that gives us constant factor approximations even for non-monotones. So we have 1 over e even for non-monotone functions. So the main question that we could ask now is, okay, this is great, but is this optimal? Is this the best we can do for non-monotone maximization? And let me mention that there's actually a very good reason to be optimistic that this is not optimal, that we should be able to do better. And this comes from the work of Buchbinder et al., who show that for cardinality constraint, we can do better than 1 over e. So we can do slightly better than 1 over e. And what we show in this work is that, in fact, more generally, we can do this. So we can achieve a strictly better than 1 over e approximation for the continuous problem subject to any downclosed polytope. And using known rounding techniques, this immediately gives us improved approximations for several classes of constraints. So for example, matroids and knapsack constraints. Good, good. So in the remaining time, I'll spend a few minutes to tell you a little bit about what we did to achieve this improvement. Okay? And for this, I want to go back a little bit to this continuous greedy dynamic that we saw. So as we saw a few minutes ago, this continuous greedy algorithm has the very nice feature that rate of increase is proportional to opt, but it's also proportional to the infinity norm of our current solution. So if our solution doesn't have high norm, then we get a much bigger gain. So this naturally suggests the following very simple idea. How about we just explicitly try to control the norm beyond what the continuous greedy is already doing? Okay? So what do I mean by that? Here's a very concrete way to try to control the norm. So instead of considering all possible directions, let me restrict my possible directions to the vectors that have norm, let's say, no more than 1/2. Okay? So instead of all possible directions, I only want to focus on those that have norm no more than 1/2. So I'm only going to update my solution using directions that have norm at most 1/2. So this is great for the norm because we have explicit control over how much we're updating. But since now we're restricting the space of directions, this could seriously impact performance. And this is the main thing that we want to understand. How does this dampening, this restriction of the norm affect performance? Okay? So what does that mean, right? So let's go back a bit and let's think about our gain. So our gain, as I mentioned before, is given by this inner product between the gradient and the direction in which we move. So for the rest of the talk, the gain of a vector will be the inner product with the gradient. So that's how we're measuring how valuable vectors are. So our gain in function value is governed by this inner product and the direction. Previously, when we had no dampening, the optimal solution itself was a candidate direction. So this allows us to get as much as the gain of the optimal solution. So this is basically the gain of the optimal solution. But now, since we only consider things that have norm at most 1/2, and opt does not, this is no longer a valid direction. So our gain could be substantially less than this. So the key point is that we need to somehow relate our gain back to the gain of the optimal solution. So how do they relate? Okay. So how do they relate? So let's, as a little bit of a warm-up, let's consider the following scenario. So suppose that in addition to opt, I have a very different solution. Let's call it opt prime. And by very different, think disjoint support. Just think disjoint support. So this solution is very different from opt, but it has a very similar gain in terms of the inner product. Okay? So let's suppose this is the case. Then in fact, we're in pretty good shape. Why? Well, because I have a pretty good direction. So what I can do is I can average out these two solutions and look at the average. So the average will have norm at most 1/2, so it's a valid direction. But since opt and opt prime have similar gain, then the gain of this direction, which is the average, is about the gain of opt. So in this optimistic case, this direction is almost as good as opt, but it has smaller norm. So we don't lose anything, and we gain over what we had before without the dampening because our norm is lower now. So we've achieved the goal of lowering our norm without actually hurting performance. So as long as this optimistic scenario is true, we're in good business. But of course, there's no reason to expect that this will be true. So it could very well be the case that opt is essentially the only solution that has good gain. Okay? But then that doesn't look too bad either, because because intuitively, then this direction V, the maximum gain direction, should be well correlated with up. Okay? Why is that? So let's think about it in this way. So imagine that I drop the dampening. And I consider this vector V hat, which has the maximum gain. So no dampening, just the maximum gain. So this vector V hat puts some mass on some coordinates, and opt puts some mass on some other coordinates. But if we look at their intersection, right? So let's say the pairwise minimum of their coordinates. So this vector here. What can we say about it? Well, so intuitively, this should be a pretty good solution. Why? Because opt was essentially the only solution with good gain in terms of the inner product. And V hat has the best gain, has the maximum gain. So if V hat is going to gain a lot, then it better have a lot of the optimal solution. So the intersection of V hat with opt better be quite good if opt is essentially the only good solution. Okay? Perfect. But you say, okay, but how does that help us? Because how are we going to find that? That's great. Well, we can just try to solve this maximization problem where we want to find a vector x that is no more than V hat. Okay? Coordinate-wise, no more than V hat. So why is that good for us? Well, because this is basically unconstrained. So if V hat is feasible, and if my polytope is down monotone, any solution less than it will be feasible. So I no longer have any polytope constraint. All I have is this box-like constraint where I just want it to be no more than V hat. And that's basically unconstrained. And in fact, that's exactly the right intuition. So we can use an algorithm for unconstrained maximization, such as double greedy, and get a half approximation. So we gain a lot more. Good. So let me conclude by putting these two ingredients together and tell you what the algorithm is. Okay. So from what we've seen, two things will happen. So we'll start dampening our solution, and for a while it will be okay. But at some point, the dampening will hurt us. And at that point, we simply want to solve this unconstrained maximization problem. And this is basically our algorithm. And it achieves an approximation guarantee that is strictly better than 1 over E. And that's all. Thank you. So I don't think it's the right bound for this algorithm, and I don't think it's the right approximation for this problem. So this is for, so we just wanted to show a small improvement just to show that 1 over E is not optimal, and we did not try to optimize it. I think if you try to optimize it, you'll get a little bit more. But to really get at the heart of the approximability, you might even require more ideas. So that's a much more interesting question.